By grouping like data types together, the storage system can make much more efficient compression decisions both when it's storing and when it's uncompressing all of that data, as opposed to what row-based engines can do. And if you think about it, it makes sense. This is because compression of integers is much different than compression of character data, or dates, or binaries, and all the other data types that are out there. Column-oriented storage units ensure that common data types exist across each storage unit. Storing more data in an overall smaller footprint because it can be compressed and still contained is a huge advantage come query time. Those large reads are now pulling significantly more actual data that again is still all relevant to my query. So we mentioned compression briefly in that first course, but let's go a little bit deeper here. Turns out you can control what type of encoding is used for the compression of your Redshift columns. Now rest assured, Amazon does have a default, but if you know what you're doing, you can fine-tune and improve from there. The compression encodings available for your request at the column level when building tables are currently, first, simply raw, no compression, byte dictionary, 256 individual bytes that can act as a pseudo-index. Great when total unique values in your column are less than 256. Delta encoding, which is basically a diff map. It's useful for storing some small integers. LZO, which is the Redshift default for anything except for bools, reals, doubles, and something that's been set as a sort key. This compression type is very effective for characters. There's mostly compression, good for storing most values in a column. The rest are left raw. The N in mostly N can be 8, 16, or 32 bytes, with the resulting compression being 1, 2, and 4 bytes respectively. This compression is really good for ints and decimals. Run length encoding, which is a traditional encoding style that replaces reoccurring values with a token, kind of like the old zip style. Text 255 and text 32K, which is good for when you have varchar columns, especially with many repeating words. And then finally, Z standard, which is a compression encoding with high compression ratio and is pretty good across diverse data sets. One of the 3 or 4 that supports all column types, and generally a pretty safe choice. These encoding types are all well documented in the online Amazon Redshift developer guide. I've put the link here. Now later in the course we'll show how you can do some deeper analysis of your existing compression with built-in queries and tools. And in the data load module, we're going to show my favorite approach of all, which is to let Redshift select the compression type, but only do so after a thorough analysis of a sample set of data on that first load using the copy command. You got to be careful because like most things in Redshift, once you choose a compression encoding, the only way to change it will be to rebuild the table and move all the data from the old structure to the new structure. So you do have to make encoding decisions wisely or stay with the Redshift defaults. But honestly, mixing the column style storage of data and compression, which is greatly improved by that column style storage, is a great benefit to the performance of Redshift. But across data warehouses, not all data is created equally, which brings us to our next topic. It's not just storage of column-oriented data that makes Redshift so fast. In fact, that's just the tip of the iceberg. Where we really see some performance, some really impressive results, is through its massively parallel architecture. So let's talk about that next.